All right, let's practice computing the line integral of a vector field, which is the topic from the last section. And I'll look at the line integral a couple different ways, and that'll motivate the concept from section 6.3, which is path independence and the fundamental theorem of line integrals. So I've got one vector field, and I want to compute the line integral of that vector field across two different curves, but the two different curves connect the same pair of points. Let's start with the first curve. I'm going to parameterize this curve with x being the parameter since y is a function of x. So I've got x is t, y is 1 over t, and t is going to range from 1 to 4. Okay, so the line integral across C1 of the vector field f dot dr is computed like this. So right now I'm carefully putting in the parameterization into the vector field. All right, now I take the dot product. Okay, I had to fix the limits of the, I didn't fix it. Hold on. I have to fix the limits of integration here. I forgot that my parameter was going from 1 to 4. Okay, there we go. And so the value of this integral is 9. Okay, so the integral of this vector field across the first curve turned out to be 9. Let me now compute that same vector field, compute a line integral of that same vector field across a different curve that connects the same pair of points. This time I'm going to use a line segment. So this was C1. Let's take a look at C2. So the trick for getting a line segment parameterized is to take 1 minus t in the first point plus t in the second point and run your parameter from 0 to 1. Okay, now that I have my parameterization, I'm going to set up the line integral of that same vector field across this C2 curve. Okay, a little messier, but let me go ahead and compute the dot product here, and I'll just have an integral in t left to compute. Okay, I really don't feel like dealing with all of that, so I just went over to Wolfram Alpha, and I plugged in the integral, and you can check to see that everything was entered in there correctly, and look, I got the same answer, I got 9. So this is sort of interesting. I had one vector field and two different curves connecting the points 1, 1 to 4, 1 fourth. And when I computed, I can think of computing this as like the work done in this force field and moving an object from here to there. It didn't matter which path I took, C1 or C2. And in fact, it doesn't matter what curve you choose connecting 1, 1 to 4, 1 fourth. With this vector field, the line integral is always going to end up being 9. So that's what we're studying in this section, this so-called path-independent vector fields. All right, here's one of the things that we're going to ask in this section. What is it about the vector field in the previous example that made this computation independent of the curve that I chose connecting a pair of points A to B? So, for example, if I changed f in the previous example from 3 plus 2xy squared, comma, 2x squared y, if I changed it over to this, for example, you can go through the previous two line integrals over C1 and C2, and you'll get different values. So that's not a bad exercise. You can use Wolfram Alpha to help you compute the integrals. But anyway, the point is, for some vector fields, the computation of the line integral between 2 points doesn't depend on the path that you take between those 2 points, doesn't depend on the curve C. But then for some other vector fields, it appears to make a difference what path you take in between the 2 points when you're computing line integrals. So, okay, we're going to try and figure out an answer to this question, and that's going to be sort of our fundamental theorem of the section. So there are line integrals of vector fields that produce different values connecting points depending if you take different curves. That's the observation I just made. But if you take a look in section 16.1, the book discusses gravitational fields and also electrical fields. And these are types of force fields that when you compute the work done in those fields from moving an object from one point to another, it turns out that they both are path independent. So let's go ahead and give a name to this path independence. So if we have a special type of vector field that happens to have this independence in its line integrals, then we're going to call it a conservative vector field. So if this line integral is the same regardless of the path you take from A to B, we call that vector field a conservative vector field. And we're going to study vector fields over certain regions in mostly R2 and R3. When I say open region, what I mean is a region that has sort of a dotted boundary in some sense. In fact, all of R2 or R3 can be considered open, but if you're looking at some sort of smaller subspace of R2 or R3, we're going to consider those that don't have a solid boundary. That's enough of an informal definition of open for our purposes. So as mentioned before, gravitational and electric fields are both conservative vector fields. Okay, and the term conservative is coming from the conservation of energy from physics. Okay, so here's sort of the answer to our question. If we have a continuous vector field on some open region in R2 or R3, then that vector field will be independent of path, so conservative in our new language, if and only if that vector field is the gradient vector field of some multivariate function. So our sort of check to see if this path independence holds is to check to see whether the vector field we're looking at is actually the gradient of some multivariate function. So if you remember, when we were first talking about vector fields, gradients were specific types of vector fields, but not all vector fields are, in fact, gradients. As a reminder of what the gradient is the vector of partial derivatives, right? So the gradient of a multivariate function is a sort of derivative of that function. And when we're saying that a vector field is conservative by being the gradient or some sort of derivative of a multivariate function, we're saying that that little f is an antiderivative of this vector field of sorts.